this case, what we have is that they give us this function, and essentially what we're going to be utilizing here is the extreme value theorem. And what I'd like to do is I'd like to get an idea of what's happening to this function on that interval really quickly. It wouldn't be very hard to get an idea. So what we're going to do is we have this, and then let's say this is 1, and then over here is, let's say, 2.5, which is that 5/2 value. And then somewhere 1.5, and then 2, let's say. Okay, and these are my x values, and then my y values out. Now, what I purposely made it so I would have this value 2. Why? Because I knew beforehand that f prime of x, right? So I differentiate this value to find any possible critical value. So a critical value a critical value is where f prime of c equals 0. Any c comma f of c. Okay, so this is a critical value, critical point. Any with this being the case, or with f prime of c not existing, but that's not what's relevant here. So I want to find the critical values for when the derivative equals 0. So that's 6x, this is my derivative, 3x squared. So what I have here is that now I want to find when it equals 0. So I factor this, the 3x can come out, I'm going to get 2 minus x. And this derivative equals 0 when x equals 0 and when x equals 2. So the critical values on this interval are only this x equals 2 value. And that essentially means that the slope of the tangent line will be 0 at that point. So the graph of f is going to flatten out at 2. Now it could flatten out and then begin going back up. It could be already decreasing, flatten out, and continue down. It could be increasing and then go back to decreasing, in which case this will be a max. It could be decreasing and then go back to increasing. And that's all the possible cases that you could have for this. You know that this function is differentiable because it's polynomial. You know it's continuous because it's a polynomial. A polynomial is differentiable and continuous everywhere. So this polynomial is differentiable and continuous everywhere since it's a polynomial. Now we want the absolute minimum of the minimum value of f on this closed interval. So what I'm going to do is I'm going to compute these key values. I'm going to compute the endpoints, 2 and 1/2, and I'm going to compute the critical values. And that's going to give me everything that's happening here. I'll be able to compute absolute minimum, absolute maximum, everything. So what's f of 1? F of 1 is going to give me 2. So let's plug in 2. Let's say 2 is here. F of 1 is 2. 1 squared is 1, and then times 3 is 3, minus 1 cubed is 1, 3 minus 1 is 2. Now let's do f of 2. So f of 2 is going to look like this. 2 squared is 4, times 3 is 12, minus 2 cubed is 8. So I get f of 2 is 4, 3, 4, something like that. And then finally, f of 2.5 is 5/2. So 5/2 squared times 3 minus 5/2 cubed. And this is the same thing as 3 times 5 squared times, so this is 2 squared on the bottom, but I'm going to multiply by 2 on the top and bottom to get a common denominator of 2 cubed minus 5 cubed. And I'm going to see what this equals. So this is 6 times 25, which is 150, minus 25 times 5 is 125. over 8. And that's 25 over 8, which is 3 and 1/8. So I have a sense of where it is. It's 3 and 1/8, which is somewhere right here. Now, this implies this last value and these 3 points together give you a shape of what this looks like on this interval, and it looks essentially like this. Okay, some nice curve with it, right? This is f on this interval, and right away we can determine the minimum value of f on this interval. The minimum, the lowest value, is 2. Now, it's tricky that they're asking us for the minimum. They could have asked us for the maximum. The maximum would have been 4. They could have said, well, I guess that would be a minimum and maximum, right? But yeah, that would be how to do this one. And you're using this extreme value theorem. And you always want to graph in this interval. You want to graph the critical values and then the endpoints, because the endpoint here was crucial, right? The absolute minimum value, the smallest value on this entire interval is going to be here. Now, how did I know it didn't go like this? How did I know f didn't go? Or better yet, how did I know f didn't go like this? So let's actually go through this again. So that's good. So how do I know f looked like how I sketched it? How did I know f didn't look like this, for example? In which case, this would be the minimum value. Well, because then there'd be another value where the slope of the tangent line would be 0, and there'd be another x value to make the derivative equaling 0 here. But there was only one x value that made the derivative 0, this point right here, which means that x can change, that f can change its direction at most one point, that point right there. So it has to look like this. There's no way it could look like anything else. And then that guarantees that not B, that 2, this is the minimum value on that interval.